Hello everyone, I'm Asude and I will tell you about the physical Cartpole, which is also known as the inverted pendulum problem. I want to start by introducing the physical Cartpole. The objective is to keep the pendulum vertical. This is the Cartpole we purchased from AliExpress. Here a PID controller is running on it. Of course, the physical system is not restricted to a PID controller. Once you have a good model of the system, you can implement different controllers and assess their performance. During the workshop, you will have a chance to learn a controller for this physical Cartpole. So why is the Cartpole problem interesting? The problem of balancing a pole on a moving cart is a widely used benchmark problem for testing controllers and learning algorithms. The reason of its popularity is due to its nonlinear dynamics, which we will see later, and its relevancy to a number of control problems. For example, personal mobility devices like the Segway transporter, orientation control of a booster rocket at takeoff, and balance control for a legged robot, all of which can be simplified to the Cartpole model. The control task of a Cartpole is to balance a simple pendulum around its unstable equilibrium point, meaning the upright position. And to do so, we can only use horizontal forces acting on the cart. Simultaneously, we want to control the position of the cart. In other words, we expect the cart to track the reference point while keeping the pole upward. This is called set point tracking. As we saw in the video earlier, the cart is free to move within the bounds of a one-dimensional track, and the pole can move in the vertical plane parallel to the track. Therefore, this system has 2 degrees of freedom. Although there are 2 degrees of freedom, there is only one cart motor to control both position of the cart and the angle of the pendulum, and this is why the system is called underactuated. Here are the second-order differential equations of the system describing the motion of the cart and the pendulum. The first equation is the acceleration of the cart, and the second equation is the angular acceleration of the pendulum. In principle, the different terms in these equations capture different aspects of the Cartpole dynamics. The first term that we see in red accounts for the gravity forces acting on the pole. The second term here is the Cartpole friction. The third term in green is the law of inertia, and the fourth term accounts for the cart track friction, and this is the effect of the force applied to the cart. So one important thing to mention about the Cartpole is that the 2 outputs are contradicting each other. In this video we can see this. I will play it for you. So here, when a disturbance is given that pushes the pole, for example, to the right, the cart increases its position error by moving the cart further to the right and making the pole lean toward the left. Then by keeping the pole slightly leaned toward the left, the cart starts moving back to its original reference point by keeping the pole upright. So here. You can observe this for the other direction as well. This is why a trivial implementation of a PID controller won't work here. Before moving on to how a PID controller works, I want to point out how we measure the states of the system. There are 2 sensors. One of them is for encoding the speed of the cart by counting the turns of the motor. This is where the motor is located, and the motion of the cart is achieved by the motor turning the track belt. And the second sensor is for encoding the angle position. Now let's see what a PID controller is and how it's implemented in the physical Cartpole. The main advantage of a PID controller is that we don't need a model of the system to implement it, because it performs simple operations on the error value and gives a controller output to minimize the error of the system. The error value is calculated as a difference of the reference point and the output of the system. The proportional term P gives an output that is proportional to the current error E. Increasing the P gain Kp typically leads to shorter rise times and also larger overshoots. The integrative action is typically employed to optimize a steady-state response of the system and shape its dynamic behavior. And the derivative action responds to the rate of change of the error signal and is mostly relevant with shaping the damping behavior of the closed-loop system. These gains, Kp, Ki, and Kd, can be experimentally found by tuning. In the physical system, because we have 2 outputs that we want to control, we are applying 2 different PID controllers and summing up the controller outputs before sending a motor command. Aside from PID, there are controllers like LQR, MPC, MPPI that rely on having a good model of the system. There are other nonlinear controllers as well that can be used to better control such underactuated systems and take into account the swing up of the pole, which is a more advanced Cartpole task. Please check out the workshop pages for more tutorials on these controllers. And I will be on hand to support data collection and experiments with the Cartpole for participants throughout the workshop.